So now we move on to our section 2, in which we were given 3 gram of a homogeneous compound that contained 3 substances: caprolactone, acetic acid, and benzoic acid, and our goal was to isolate them in their purest form. So we are going to discuss what technique did we use and how did we isolate the 3 compounds in their purest form. The technique that I used was taught in our organic chemistry labs, and that was liquid-liquid purification. So the first step was solvent selection. Now, an appropriate solvent would be the one which would dissolve all of 3 substances very well and would stay immiscible in water. So according to me, the best solvent for that one, for my 3 compounds, was dichloromethane. So we mix our homogeneous mixture into dichloromethane and then put it into a separatory funnel, after which we add some water and base. Now, the reason for adding base is that the acids that is in our compounds would get deprotonated, which would make them much more soluble in water than in organic clear. But caprolactone would not get deprotonated and is still better dissolved in our organic layer. Here we can see that dichloromethane is denser than water and hence it's at the bottom of the funnel. Now we first separate our organic layer, and with that we separate our caprolactone from our acids. Next we take our aqueous layer in a different beaker. Now because we have to wash our aqueous layer, we might need to put it back into a different separatory funnel and add a brine solution to remove any aqueous impurities. Now, moving on to removing caprolactone in its purest form from our organic layer, we need to introduce our organic layer into a rotowave machine. A rotowave machine is used to distill out the solvent, leaving out the pure compound behind. So, after the procedure of rotowave, we would get our caprolactone in our purest form. Now, before we put the organic layer into rotowave, we add a drying agent in it so that we can remove any left out aqueous impurities that might be present after the process of extraction or washing. The drying agents are numerous, but the one that we use would be sodium sulfate because it is available very easily. It is easy to use for the students and is also inexpensive. Now, moving on to our aqueous layer, there are 2 ways that I came up with which we could use to separate the benzoic acid and acetic acid in the purest form. The first one is that we let it cool down at room temperature and start adding acid, which would protonate our benzoic acid and acetic acid. Now, benzoic acid at room temperature is insoluble in water because of the 6-membered ring that it has, while acetic acid, because it has a shorter hydrocarbon chain, it is very much soluble in water even at room temperature. So once at room temperature benzoic acid starts to precipitate, we can use suction filtration or maybe gravity filtration and remove our benzoic acid. After that, we can put our acetic acid in the aqueous layer into an ice bath. When the temperature reaches below 16 degrees, the acetic acid would start precipitating, after which we can perform suction filtration to remove our acetic acid. The other way that we can do it, that we can follow up to remove the acetic acid and benzoic acid, would be by adding the base and with that carbon disulfide. Now, as I said, benzoic acid would not be soluble in water at room temperature, but it is very much soluble in carbon sulfide at room temperature. So this is just like performing our liquid-liquid separation again for our acids, because we form 2 layers, organic layer with carbon disulfide and benzoic acid and an aqueous layer with acetic acid. So once we separate our organic layer with benzoic acid, we can put it into a rotowave machine and we can distill out the solvent and we can get pure benzoic acid, and we can isolate acetic acid by putting the solution into an ice bath and it would precipitate out below 16 degrees Celsius, after which suction filtration can be done and we can get our acetic acid in the purest form. So this is the method that we could follow to get both of our homogeneous mixture into their purest, all 3 of the compounds from the homogeneous mixture into its purest form. Now we'll move on to our segment 3. In the segment, I'm going to discuss about organic synthesis lab. We are going to discuss the procedure, analyze the product, and are going to discuss thoroughly the mechanism that the reaction might have followed. Now, first, we'll discuss the procedure. So, our aim was to uh, obtain 2-butoxy naphthalene from 2-nephthol and iodobutane. So, first, we start the experiment by measuring around 0.56 grams of 2-nephthol and putting it into a round bottom flask. We add NaOH pellets, we add a stirring bead, and we add ethyl alcohol that we have chosen as our solvent. After we have done this, we put the flask onto our hot plate and we put the whole setup into a fume hood. We start the reaction by letting the solution heat up and starting the solids to dissolve. We see that at first we have a dark brown color liquid in the flask, but as the reaction starts proceeding forward, we see a bluish black color liquid that has been formed. This might be transition states or maybe any intermediates that were formed. Now, as soon as all of the solids dissolve, we add our iodobutane to it. The reaction that will follow now would be a reflux reaction. In this, we can see that our bluish black color solution, as the reaction moves forward, turns into yellowish and then golden brown. At this point, we know that our reaction is complete, and hence we take our round bottom flask off the hot plate. Now, before moving forward, we do a TLC analysis, the results of which I'm going to discuss into our product analysis part. So after the TLC analysis has been performed, we put it into an ice bath, and this reaction in the ice bath is called the quenching reaction. Now we see that our golden brown solution starts turning creamy brown and the crystal starts to appear. Then we perform suction filtration and we can isolate our final product, that's 2-butoxy naphthalene. And this concludes our procedure for organic synthesis. Now we'll move on to the analysis part. So the product that we obtained was a creamy brown colored crystals, uh, and they weighted around 0.26 grams. Now I'll discuss the TLC analysis that we performed. In the TLC analysis, we saw that there were two yellow spots on the reactant side and on the co-spot lane. We also saw that there were distinct purple spots on both our reactant and co-spot lane. We saw that the yellow spot was not present on our product lane. This might mean that maybe the impurity it was an impurity that was present at the start but is not present anymore in our product side, or maybe it represented the reactant itself, but we see a separate distinct spot on the product lane too. We saw a light spot that represents two spots on our co-spot lane and our reactant lane too. This might also indicate the reactant and might indicate that the reaction did not complete completely. Now we are going to discuss the reaction mechanism that the reaction might have followed. We are going to discuss four criteria. The first one is solvent. The solvent that we chose is ethyl alcohol, and it is a polar protein solvent which is generally used in SN1 mechanism, which might indicate the reaction might have followed an SN1 pathway. But anyways, moving forward, we now see our nucleophile. So the nucleophile was formed when we added NaOH to 2-nephthol, which formed a nephoxide ion. According to me, nephoxide ion is a pretty good nucleophile and it can attack an electrophile efficiently. Now, we are going to discuss about the substrate. The substrate here is iodobutane. It is not a bulky substrate, which means that this reaction might be an SN2, because in SN2 reaction we choose a substrate that is not bulky so that the nucleophile can attack our electrophile efficiently. So this points towards an SN2 mechanism as well. Now next we discuss about the leaving group. The leaving group in our case was iodide ion. I think iodide ion can efficiently spread and stabilize the negative charge that it has on it after the reaction, because it is an electronegative element and it has way larger orbitals which can easily spread and stabilize the negative charge. So maybe our first criteria that the solvent uh, pointed towards SN1 mechanism, but the rest three criteria pointed towards an SN2 mechanism. So I came to a conclusion that the reaction mechanism followed by our reaction was an SN2 indeed. Okay, so now we are in our final segment of our video, in which we are going to discuss about various purification and characterization techniques that were taught to us in our organic chemistry labs. The first one of which is recrystallization, which we have performed to isolate a pure unknown solid that was given to us. So the first step in recrystallization is solvent selection. An appropriate solvent is the one that would not dissolve our mixture at room temperature very well, but would dissolve it very well when put in an heat bath. So once the solvent's been selected, we start dissolving our impure solid mixture. We do this by adding the mixture into a flask and then adding our solvent and then start to heat it. Once we see all of our impure mixture has dissolved, it would leave out some of the insoluble impurities. Now to remove these, we perform gravity filtration, in which all of our insoluble impurities are taken out and we obtain a pure solution of our solid. Now we let it cool down at room temperature before putting it into an ice bath, and when we put it into an ice bath we leave it undisturbed. This is done so that we can obtain larger crystals which are easy to isolate and are appropriate. So once we put the solution into the ice bath and we see that appropriate crystals have formed, we use gravity filtration to isolate them, and in this manner we get our pure solid from our impure mixture. The next technique that I'm going to discuss about is distillation. In distillation, we try and separate two substances that have different boiling points. There are various kinds of distillation. I'll tell you about three of those. The first one is simple distillation, in which we separate compounds that differ in their boiling points by more than 100 degrees Celsius. If the difference in temperature is less than 100 degrees Celsius, we use fractional distillation. And if we want to remove or isolate a water insoluble substance, we use steam distillation. So in our organic chemistry lab, we were given a mixture of two substances with different boiling points, and we use simple distillation to separate this. This is just a basic setup of how distillation should look. So first we have our distillating flask, in which we have the mixture of our solution of two substances, mixture or solution of our two substances. So the first step is to start heating the solution. As soon as we start heating it, we see that the temperature starts rising and the vapor condenses on the walls of the flask, on the three-way clamp, and even on the thermometer. Now, as long as the vapor is passing through the side arm, we know that it is in equilibrium with the liquid that's condensed on the thermometer, and this would give us an appropriate reading on in our boiling point. So once we see that the temperature starts increasing significantly, we let the distillate collect into our receiving flask, but at a point when it becomes steady, that is, it does not vary for more than 1 or 2 degrees Celsius, we change our receiving flask. We put another vessel, because now we know that the liquid A, which had a lower boiling point of the substance, is gonna come out of the sidearm. Now we let the receiving flask collect our unknown liquid A until the temperature does not vary significantly, that is more than 5 degrees Celsius. When that start to happen, we remove our receiving flask and put another one in place, because now we know that whatever is going to come out of our sidearm is not the liquid that we desire. Again, when the temperature reaches a stationary point that is not varying by more than 1 or 2 degrees Celsius, we start collecting our liquid into a separate vessel to obtain our solid B that might have a higher boiling point. So in this manner, we obtained two liquids or two substances using their different boiling point in their purest form. So this concludes our purification techniques. Now we move on to our characterization technique. The first one is melting point determination. So in melting point determination, we use the principle that two different substances will have two different melting points, and if one substance would have a pure substance would have a melting point that does not vary by 1 or 2 degrees Celsius. So we can compare the melting points of our unknown with the literature melting points of our suspect. If both of them match, we can say that our suspect is the substance that is our unknown. We could also get a mixture of our suspect and our unknown and start to melt it. If they melt at the same temperature, we know that the suspect and our unknown are the same. Similar principles is used for our boiling point determination too, that two different substances would have two different boiling points. If the literature boiling point is same to the experimental boiling point, the two substances might be the same substance. Now next we move on to our next characterization technique, that is TLC, thin layer chromatography. It works on the principle that there are two phases. One is a stationary phase, that is our absorbent, and one is a moving phase or mobile phase, that might be our unknown substance or a liquid substance or any gaseous substance. Now we start our TLC by choosing the appropriate absorbent, because every absorbent would have different absorbing varieties, because not every absorbent would absorb same different substances in the same manner. Now at first, we break our capillary tube. We divide it into two pieces by burning it or melting it from the center using an ethanol burner. We do this so that we get two pieces, one which can be used to collect our unknown and one which we could use to collect our suspect. After this, we prepare our TLC plate. Our TLC plate is prepared by making an origin line and 3 points that represent 3 lanes. First is our unknown, second is our co-spot, which has a mixture of our unknown and suspect, and the third one is the only suspect. Once we have prepared our TLC plate, we introduce on the TLC plate our suspect, our mixture of substrate and suspect, and our suspect in the third lane. Now we put this into our TLC chamber, which contains our solvent. Our solvent are mostly organic substances, because they are better absorbed by the absorbent and would compete with our unknown substances, our suspected substance, to be getting absorbed by the absorbent. So now we wait until the solvent rises to a point where it is below 1 centimeter below the top of the TLC plate. At this point, we remove our TLC plate that we developed, and we see that the topmost point that the solvent reached and mark it as the solvent front. Now we calculate the distance between our solvent front and our spots, which gives us the RF values. Now, two substances, if they have the same RF values, we can assume that they are the same compound or substance. So if our suspect's RF value matches our unknown's RF value, we can characterize them as a same compound. Similar to TLC, we have gas chromatography. It also works on the principle that there is a stationary phase and then there is a mobile phase. But in our gas chromatograph, we use a gas chromatograph machine that gives us a gas chromatogram, which has several peaks, which represent several substances that were put into our gas chromatograph machine, and the area under the peak gave us the amount of substance that we put. Now, instead of observing the RF values that we did in our TLC, we observe our retention time. Retention time is the time taken by a particular substance to exit the column, and every substance would have a specific retention time. If two compounds have same retention time, we can assume that they both are same. So if our suspect has the same retention time as our unknown, we can characterize them as a same substance and make an assumption that they might be the same. The final characterization technique that I'm going to talk about now is IR spectroscopy. So in our IR spectroscopy, we use the principle of the light absorbed by a particular compound, and that the bonds between the individual atoms in the compound would stretch and give us a specific peak at a different wave number. So we use IR spectrometer to get IR spectrum, which has several peaks at different wave numbers. We can determine what functional group the compound has using the peaks, because we have a table that provides a specific peaks at different wave numbers for specific functional groups, and then we can match those peaks and can come to a conclusion of what functional groups might be present in our compound. We can also compare an literature our spectrum for a suspected compound with the one that we obtain in our lab for our unknown. If both of them match, we can say that they are the same substances. One more thing that I would like to add, the peaks represent the bond stretching of the various elements or the various atoms in the compound, and we use this principle to get our IR spectrum, and then we can compare various IR spectrum to deduce a conclusion and assume what the unknown compound might be. So that marks the end of our video, and hopefully it provides you with a better understanding about the governing principles behind the techniques and the procedures that we had followed in our organic chemistry labs. Thanks for watching and have a good day.